Today's topic is a very fascinating one. It sounds a little controversial. Maybe it's intended to be so. So the topic is the death of traditional modeling and the rise of deep learning. And we are fortunate to have with us today Keenan Moukarzel. He's going to be our speaker. Keenan is a published scientist, inventor, entrepreneur, and data analytics business lead for a Fortune 50 company. His current job involves applying the latest machine learning techniques to improving and augmenting Freddie Mac's business operations for single family. In 2019, he co-founded the Python Academy, very impressive, where he organizes and teaches classes in data science to anyone looking for a career switch or looking to learn Python from scratch. Keenan also publishes in the popular Towards Data Science blog. He's an avid learner and a big proponent of AutoML. He's also an early adopter of the Data Robo platform. So it is my pleasure to welcome Keenan to our virtual meetup. Thank you, Keenan, for joining us, and it's all yours.
Thank you so much, Pramod, for the very kind introduction. So I am going to share my screen here. So thanks again for having me, Pramod. It's a pleasure and honor to be here. I was looking at the list of participants earlier. Very thankful for you guys to join. For those who have who know me from before, and for those who have not met me, thank you as well for joining. My name is, like Pramod said, Keenan Moukarzel. I'll just briefly establish my bona fides here, so you guys know a little bit of my background. And then I'm going to ask you guys to introduce yourself as well in one line. But if it's going to be a bit difficult, as Pramod and I mentioned, we're discussing earlier, you can use the chat if I'm able to see it. Otherwise, that is totally okay. Or you can use maybe the Q&A as well, just to see sort of your reactions, because I like to sort of interact with the audience, if possible. If not, that's totally okay. I'm happy to talk to myself. So I work at Freddie Mac, as Pramod mentioned. My official title is Data Analytics Business Lead in the Operational Modeling and AI Application part of single family. And so my job consists of finding opportunities, business opportunities, where we can leverage AI technologies, machine learning, and all of predictive analytics or augmented analytics to sort of enhance single families business operations, right? I've implemented 2 models in production. One of them we're going to file a patent soon for, data matching service, and I just implemented one that checks for secondary financing for in some of our portfolio loans. Love Freddie Mac, great company. I've learned most of the stuff that I know today thanks to Freddie Mac. So on the side, I founded, as Pramod mentioned, the Python Academy. I'm a huge Python guy, and contributed a lot of my success in my career so far to Python because it really helped me automate a lot of the stuff that I was doing, in addition to obviously the data science that you guys are all familiar with that you can do in Python. Python can do so much more than just data science, including automation, web automation, website creation, and all other things I don't want to get into right now. Lastly, I publish in Medium in a fairly, good cadence every week or 2 weeks. You'll see an article from me. So if you like, what you see today, I publish there. So please comment on the stuff that I write there. I'd like to learn from you guys as well. So I like this to be a two-way thing. So that's the self-promotion part of the presentation. So we got that out of the way. It's about you as well. So I do want to hear a little bit about you. If you can just, if possible, Pramod, tell me if not, but if in just one line, just tell me your name and sort of your background, like what are you interested in, just so I can kind of gauge the audience to see if I should talk more technical or more not technical, right? Because there's always these two aspects. I don't want to bore the audience too much if you guys are non-technical. Awesome. Isaac. Hey, Isaac. Thanks so much for being here. We have an actual bioinformatician from worked at the NIH before. Actually, a friend of mine, Isaac, is here. I love having really good discussions with him as well. Aaron, how are you doing, Aaron? Awesome. You're looking into data analysis. That's great. Aaron was at the ODASC as well, so it's good to see you again, Aaron. Nishant, how are you doing, Nishant? It's good to see you again. Pursuing your MS in industrial engineering, okay. And data science, you have an interest in data science. Okay, that's good. We're going to talk a lot about data science. All right, I think that's good for now. If you want to, please keep putting in the chat. I have the window right here, so my presentation is here. My chat window is here, so feel free to type in at any point during this presentation. So today's topic, we're going to talk about machine learning. So the title is The Death of Traditional Modeling, the Rise of Deep Learning. I use these terms specifically, and I'm going to put them in context just a little bit, but obviously the topic machine learning is closely tied to all these other peripheral topics, which include artificial intelligence, neural networks, you see the technology, and all these other things, right? But the core topic is going to be machine learning, right? It's a hot topic. It's been hot for a little bit. And I want to start actually, I was actually talking to Pramod earlier that we're really living in very fast-paced times, like the very changing time. Things are happening so quick, especially in the field of machine learning and artificial intelligence. And so what I've done is I looked up Google Trends because I was working. I've been in the industry, at least more industry for the past 6 years. Been working for the past almost 10 years, and artificial intelligence hasn't always been a hot topic like it is today. And so it's only been recently, right? And if you look at the trends for machine learning and artificial intelligence, and I started in 2005, I'll probably go further back, but if you start 2005 to date, you'll see that for the majority of the time, the interest in machine learning and AI has been kind of constant. And then something happened in 2015 and 2016 in that era. So 2015, you had a little peak, and then 2016 hits, and then you have a massive uptake or massive increase in the interest in machine learning and AI. And it's not just an increase, it's a sustained increase, right? So it went up and it kind of sustained. So it kind of stayed fairly hot. And so my question to you guys is, what do you think happened in 2015 and 2016 that caused the hype that we are all living in today? What events, major events, happened in 2015 and 2016 that caused us to be now living in a world of AI? And every other ad on my LinkedIn is about AI, probably because they're targeting me, but any guesses goes in the chat. If not, that's okay. I'll give you guys the answer in 10 seconds. 2015, 2016, something happened, something big. Alrighty, it's okay if you don't know. And I'll tell you at least the way I lived it. So what happened is AlphaGo. Okay, AlphaGo, a company called DeepMind, achieved what many in the field perceive to be the holy grail of artificial intelligence, which is beating a top professional player in the game of Go using a machine learning algorithm. No human touched the game. It was literally man versus machine. And it was a truly groundbreaking event, and I'll tell you guys why. AlphaGo truly is the godfather of modern AI, modern meaning in the past 4 years. Everything we're seeing today, AlphaGo has definitely helped shape. And let me explain why. So if you guys don't know what Go is an ancient Chinese board game. It's essentially, if you can see at the top right here, 19 by 19 board with black and white stones. So it's 2 players playing. And the objective of the game is to capture as much territory as possible on the board. And the player with the most territory wins. It's not as simple as that because you can capture stones and capture territory. So there's a lot of fights that can happen. But it's essentially a board game I wouldn't say similar to chess because it's a lot more complex, but essentially, the beauty of Go, one of the things that was charming, is that it was considered extremely difficult for a computer to beat a human at the game. Although the rules are very simple, the problem and the main difference between this and chess is that the number of possible games in Go is greater than the number of atoms in the universe, meaning that there's more possible games of Go than there's atoms in the entire visible universe. So if you want to have a strategy where you're going to look at every possible combination of moves and then you're going to go with the moves that are most favorable to you, you're going to be out of luck because it's physically close to impossible to compute that many computations. Unlike in chess, it's a lot easier to do so. What we call exhaustive searches, right? You're just going to look at every possible potential move in the future and then play the move that favors you more. So you can see in this article, The Mystery of Go, the ancient game that computers still can't win. That was published in 2014 by Wired Magazine. And so it's always been considered the holy grail of artificial intelligence. And so when AlphaGo came and actually beat the world champion in March of 2016, that sent out shockwaves to the world. If you watch the documentary, you will see the amount of publicity that this received, at least in Asia. Even in America, you see articles from the New York Times, the Atlantic, and like literally every source that is sort of really amazed at how Google was able to perform this. And you can see here they called it even Google's computer program. They didn't even know how to call it. They didn't know it was artificial intelligence or anything like that. They just called it Google's computer program beats Lee Sedol. That was just 4 years ago. And so it rocked the world. It won 4-1. There's one game that the human was able to win that gives hope to humanity. I don't want to get into it right now, but definitely a groundbreaking event. And not just that, AlphaGo kept going. It won against a ton of other world champions as well. So it's not just by luck that it beat Lee Sedol. It beat all the other world champions. And after that, they essentially published a paper, a very famous paper, and I highly recommend reading it. In the Nature, a very prestigious journal. And there they outline how they did it, what their strategy was. And it turned out that AlphaGo used artificial neural networks to learn from thousands of games from professionals that they collected online, and they actually fed that into a neural network. Now, not just any random neural network, they actually had a very good design for their neural network. They had two networks, essentially, that work together. A policy network that looked at strategies locally, and they had a value network that did strategies on the entire board. So it's not just about, your best move here is this. Is that the best move in the entire board as well? Because you have to look at things macroeconomically, not just locally. And so very, very nice paper, groundbreaking again. And the good thing or the bad thing or the interesting thing here is DeepMind didn't just stop there. DeepMind thought, well, with AlphaGo that beat Lee Sedol, we're able to do it by using thousands of professional games. What if we just don't give it any games at all, and then we let it play against itself? Okay, so instead of having it learn from previously played games, it's just going to say we're not going to have it play any games, learn from any games at all. We're going to have it essentially play against itself. And so they call this AlphaGo 0, because 0 means they started from scratch. So AlphaGo 0 played against itself for a few days, and after just a few days, it accumulated the equivalent of 3,000 years of Go experience. And then AlphaGo 0 played against AlphaGo. And then AlphaGo 0 won 100 games to 0 against AlphaGo. And that was another huge accomplishment, how reinforcement learning was able to beat supervised learning in a way, right? Essentially, we remove the human bias. Reinforcement learning is just a machine learning against itself, versus AlphaGo, the previous version, was learning from humans and then applying this against another human, versus here is just learning about itself. So groundbreaking thing happened all 2016 and 2017 for AlphaGo 0, 2016 for AlphaGo. That really sent shockwaves, and this is where machine learning as we saw the trends start really picking up in the news. And as you know, with new topics, new things, new grounds, new possibilities, comes a lot of chaos, right? It's like the El Dorado now. Everybody's like, whoa, this is what they're accomplished with machine learning. And you had all these other things too, like, Google uses technology and then came up with all these great products. Image recognition picked up all these things. And all the cool things are, by the way, using neural networks, right? No traditional modeling. But anyway, so all these new novel topics will bring in a lot of confusion, but also a lot of really cool topics. And as you can imagine, billions of dollars in marketing and advertising starting being poured into the whole topic. It's like, whoa, machine learning, AI, let's just ride that wave. And so what happened here is when you have a lot of interest, a lot of money, you have a lot of polluted airwaves, right? A lot of misused buzzwords. You have also a lot of synonyms, a lot of words that are used or invented just for the heck of it, like augmented analytics. You guys have heard about that one. That was invented by Gartner just a couple of years ago. And it's essentially predictive analytics, very similar, but uses special machine learning techniques. I don't know how they spin it off, but everybody came up with their definitions. Everybody started to understand what the topic is and the definitions and things like that. So there's a little bit of confusion. And so when I talk about traditional modeling versus neural networks, I want to be very precise, right? And I want to make sure I'm not like talking about these conflations. But as also, again, you have new topics coming in, you have also a lot of people who try to box things in, right? Try to put definitions around things, right? So a definition around artificial intelligence, around machine learning, around deep learning. Even artificial intelligence, the definition changes. I'm sure you've heard maybe 10 different definitions, right? Different definitions of machine learning. But generally speaking, what I see a lot, if you ever took a class in machine learning or a class in AI or anything like that, you will see a lot of people talk about these three circles and say yay in the chat if you've seen these before, or you might have seen a version of these. Essentially, it says that the field of artificial intelligence is vast, and machine learning is a subset of AI, right? AI is big, and then you have machine learning, which is a subset of AI, and then deep learning is a subset of machine learning, which is a subset of AI, okay? And then you have some versions where people want to add an extra circle here for data science, or they want to add, hey, everything is part of programming, guys. Okay, so here's the software engineers. I'm sure it's a software engineer who came up with this one. You guys are all just doing programming, children. And then you have here also fancy charts and all this thing. But essentially the concept is, and you can see it, you've probably seen it before, but AI, machine learning, deep learning, okay? And this is where some of our issues might come around and some of the confusion. And let me explain. So let me sort of break the bubble here, okay? Let's talk about artificial intelligence. So the claim here is artificial intelligence is this vast field. Machine learning is a subset, but it's not the whole, right? And so my question to you guys is, if artificial intelligence is not always machine learning or doesn't use machine learning, can you name me a technique that artificial intelligence uses that is not machine learning? So any AI technique or any AI concept or any AI product that you guys know that you would qualify as artificial intelligence, but that does not use machine learning. Do you guys know of anything like that? Again, if you have any answers to that, we'd love to see it in the chat as you guys did earlier. I'll give you guys like 20 seconds. They're tough questions. I'll give you guys that. Sometimes you want to think about them, right? An AI technique or an AI concept that does not use machine learning. Or is machine learning and AI exactly the same thing? If that's okay, if that's what you think, that's fine. I don't personally think so, and I'll show you guys a few examples. Okay, it's okay. All right. Okay, here we go. Ali. Many traditional robots use analytical solutions and laws of physics instead of learning from data. That's a good one, yes. So simulations using physical objects. So simulation of physical worlds, yes, that's a simulation that does not use machine learning per se, meaning predictive analytics. So you just let things go around and rotate. That's a good one. Thank you, Ali, for that. Appreciate that. So that's a good example. And I'll give you guys a couple of examples here. So anything that has very good logic or very smart if and then statements, or even very smart software programming can be labeled as artificial intelligence without using any machine learning. I'll give you guys 3 concrete examples of that. The first one is a game engine. So I picked StarCraft here, but I'm sure you guys have played old style games. So StarCraft came out in 1994, for example. StarCraft, the premise is you gather resources, you build a base, you build an army, you attack the opponent, and then you win. You could be attacked yourself, so you have to manage your resources, you have to manage your defenses, but also attack. It's fairly complex, but essentially when you want to play against the computer, you played against an AI. And the AI computer is actually fairly smart and fairly difficult to beat. That it takes you quite a few rounds playing the game to be able to defeat the computer or the AI. And the computer AI did not use any machine learning. It's just very smart programming. In fact, the guy who wrote the AI, the computer AI who can play StarCraft, just locked himself for 2 weeks and did it. Literally locked himself for 2 weeks and just programmed it away. It's a lot of if and then. It's a lot of loops, so while loops and things like that. But that did not leverage any machine learning. Same with the Google search engine. For the majority of its life, Google search engine does not leverage any predictive modeling. It's just a lookup engine, right? So it has a web crawler, goes around, checks the website that has the most, if you do a search, it'll just pull up the website that have the most keywords with indexing and things like that. Did not use any machine learning for the most part, right, until the past 5 years, right? So we're talking about back in 2010. And even in 2010, 2012, you always thought Google was smart, right? Google knows what you're looking for. Google it, right? That came over a decade ago, and Google just wasn't the search engine I'm talking about. Did not use any predictive modeling, but it was smart. So you could qualify that as artificial intelligence because it kind of knew what you're looking for. Autocorrect, also the first versions did not use any machine learning. Nowadays they do, but the first ones used Bayesian search theories. So a lot of it did not use any machine learning. So these are examples of artificial intelligence, but that don't leverage machine learning. And Ali also gave us another one as well. So I'm comfortable with the idea that artificial intelligence is this vast field, that it's not necessarily about machine learning. So machine learning is great, but you can have artificial intelligence without having necessarily machine learning in it. Now let's talk about machine learning. So a lot of you guys do machine learning. I know that because I know some of you. And so when it comes to machine learning, can you guys name me some machine learning techniques that you guys are familiar with, or your favorite machine learning technique? Or if you don't know about your favorite, if you're not into machine learning, you don't use machine learning, maybe give me what you think is a machine learning technique. Again, in the chat, again, I'm making this as interactive as possible, so I'd love to hear from you. So if you can just shoot out just a machine learning technique that you use at work. I'll give you guys 10, 15 seconds. Random forest, SVM, k-means, clustering. Awesome. Thank you, Isaac. I think we did discuss the k-means clustering that you've done when you're at the NIH. That's pretty awesome. Thank you very much for that. Anyone else had any other techniques that you use machine learning for? GANs, autoencoders, okay. Thanks, Nishant. I think that's good. I think we have enough here. So thank you guys for that. So when you think about machine learning and what you will learn, or at least the way it's categorized, is you have 3 types of machine learning, right? You have the supervised, you have the unsupervised, you have the reinforcement learning. And within supervised, you have classification regression techniques, and under unsupervised, you have clustering. So here we have the k-means that Isaac mentioned. You have a whole other bunch of different clustering algorithms that you can use. Under regression for supervised learning, you have linear regression, GLMs, support vector machine, here the regressor, the machine for classification, decision trees. For classification, you have naive Bayes, nearest neighbors. Thing is, logistic regression falls in here as well. So that's basically, I think we have an understanding, and I think we all agree. So machine learning has all these subfields, and within each subfields here are the different techniques. Now, I'm going to ask you guys this question. What is the problem with this particular view, right? This is the accepted view nowadays, right? Which is, that's how machine learning is classified essentially. Now, what could be a problem with this classification of machine learning, or this sort of the way we're saying what machine learning is? Is there any logical problem with this? If you think it's good, it's good. I have no problem with that. I'll just share what I have quarrels with that sort of thinking. Choosing the right technique, yeah, it's always a struggle. Which technique to use, and that's why, as Pramod said earlier, I'm a big fan of AutoML. AutoML will essentially run all these techniques, and essentially will rank which technique is better than others, right? It'll just tell you based on your own choice of loss function which technique is better. So yes, choosing the right technique can be sort of a headache if you don't do AutoML. That is a problem, but the problem I'm more referring to is that if you use any of these techniques that I mentioned here, or any of the techniques that you guys mentioned, that means that you are doing machine learning, and therefore you're doing AI. Okay? So if I perform a linear regression on a data set, what have I done? I have done a machine learning. I've created a machine learning algorithm, and therefore I've created an AI entity. And if you don't trust me, if you don't trust my logic, let's go back to this chart here, right? That says machine learning is part of AI, right? So all machine learning is AI. Not all AI is machine learning. That's what these circles mean, right? And so by saying, yes, all these are machine learning techniques, we're essentially saying these are not only machine learning techniques, they're also AI techniques. So the statement that I'm doing a linear regression is me doing AI, according to everything we just discussed, which is the mainstream view, makes it logical and sound. Now, personally, I have a problem with that because what's the consequence of us thinking like that? We'll say, well, if doing linear regression, sorry, picking on linear regression, even SVMs, if you do an SVM, does that mean you're doing machine learning? Yes, then now you're going to have all the companies in the world doing AI, right? Everybody's now into AI because I can do linear regression, I can do AI, or I can do an SVM, I can do AI, and now you have all these advertising that will bombard us. And Excel probably is the best AI software out there because it can do really nice linear regression, right? But my first point here is, and we're talking about traditional modeling, is most of these techniques are not novelty, they're not machine-based, and they don't necessarily came around the time of machines, right? So naive Bayes came out, at least the principles, the applications have been definitely refined over time. A year after Bayes' death, Thomas Bayes, linear regression first appeared in 1805 by Adrien Marie Legendre, and then you had in 1845 logistic regression, logistic growth came using the sigmoid function. That was Pierre-François Verhulst. Decision trees came later in 1959, at least the modern version, right? Support vector machines that I saw in the chat earlier, that one came in 1992. So it's fairly recent, right? The person who invented it is still alive. I looked it up. Vladimir Vapnik. 1995 came random forest. So that one you can say is definitely was definitely used or invented with the help of machines. So by Tin Cam Ho. And so why do I have a problem with that? First of all, I don't believe that linear regression is AI. And I'll tell you guys where I think the problem is. The problem, I think, comes from the word learning. So when you say machine learning, okay, so those very smart marketing folks who said, well, linear regression is machine learning because you are learning from the past to predict the future, right? And you're using a machine to do it. So you're learning about the past and you're predicting the future. Therefore, anything that uses the past to predict the future is going to be a machine learning if you do it on the machine. That's their thinking. And so now they bucketed all these things into machine learning, including linear regression, including all these algorithms, and now all these are machine learning, and therefore all these are AI, which is where you're getting all this confusion. Everybody talk about AI. I do AI now, which to me is a bit overblown, and there's this is where I think some of the confusion comes. When I hear learning, I think of two things. I think about trial and error, and I think about data updates the paradigm, updates knowledge. And I think about, like, say, I want to learn the piano, right? If I want to learn piano, it doesn't mean I'm going to look at the piano and be able to play the piano on day one, right? It means I'm going to start playing and I'm going to make a lot of mistakes, and then I'm going to have someone correct me and say, no, you should play that note, you play it that way and that way. And this is how the learning occurs, which is trial and error experience. And as you get new data, you change your paradigm, you change the knowledge, you update your parameters. And this is how you learn. And to me, the concept of having this trial and error is core to learning. And going back to linear regression and support vector machines, these things, if you look at the definition of learning, there is no trial and error that occurs when you apply linear regression, right? Essentially, you do it in one go, right? You apply a mathematical function, a statistical function to the data set, and then you get this one line, in the case of SVMs, this one line that will literally separate two data sets in the most perfect way, which is where the distance between the support data points are actually, the line is smack in the middle, right? There's no such a thing as a trial and error. There's no such a thing as learning. Learning doesn't occur with SVMs. Is there anything such as epochs? There's no epochs, right? In linear regression, it's not like you're going to try value A and then slowly adjust it, right? So the learning aspect doesn't occur, which is why, in my view, instead of calling linear regression, for example, a machine learning technique, I would personally call it machine-powered statistical regression. You look up the definition in Wikipedia of linear regression, it is still statistical regression, which is not necessarily a machine learning, meaning the machine is not learning from the data in the sense of learning. It's just looking, it's fitting a line in the data. And this is where the controversy comes, Pramod, that you mentioned. So some people might see as learning. I personally, and I know a lot of people feel that way because then we're all, AI experts, right? So the idea of learning and why neural networks are actually learning, there is trial and error, and neural networks actually go through trial and error. And they always readjust their parameters based on the data and the data only. And so the whole idea behind neural networks is that you start with an initial hypothesis, okay? And then the weights are iteratively adjusted by the data as it passes through the network, okay? And the way the weights are readjusted every time is through gradient descent, okay? So the weights are changed based on the gradient descent, and it does take practice. So if you just run one data set through if you run your entire data set through the neural network, this is called one epoch, and you're only going to adjust your weights afterwards, right? And then you adjust, and then you repass your data set, and then you readjust the weights, and you pass the data multiple times. There are definitely techniques to avoid overfitting, like dropouts and things like that. I'm not going to get into it, but the concept here is gradient descent is the learning, okay? And it mimics how you and I actually learn. So if you look at our brain works with neurons, right? You have neurons in your brains, and all your neurons are interconnected. And you have different types of connections. You have neurons that go in as input, and you have output neurons, right? And they can take different shapes like this. And sometimes you have multiple neurons connected to one neuron for output. And sometimes you have neurons that not only move forward, but also there's a feedback loop. So the neuron not only goes forward, but it also goes around backwards, and the output becomes the input. Okay? Now, the reason I put this one out there, I didn't remove it, is because we actually have a neural network type that does this. Now, whoever guesses this really will get my admiration. What type of neural network is it? What's the name of the type of neural network where you have the output becoming the input within the neuron? Where there's a loop, a feedback loop that gets fed back into the network. Ali, excellent, man. You have my admiration. That's it. Recurrent neural networks. Ali, I am a big fan. I'm going to follow you after this. Yes, RNNs and there is such a thing in nature, right? So RNNs is where the input becomes the output becomes the input as well. But you have all types of actual natural sort of connections in your brain that we can actually sort of mimic with neural networks. Another one that is very, if you look at this neuron, for example, you have 3 input neurons and 1 output neuron, right? And all 3 have to hit here. I'm looking at time here, 8:40. I'm running a little over time. Hopefully, Pramod, if I can take 5 to 10 minutes, is that okay? Or hopefully you guys are enjoying this.
Yeah, that's perfect, Keenan.
All right, thank you so much, Pramod. All righty. Hopefully you guys are not too bored. I'm not boring you guys out. But some really cool concepts are coming up here about neural networks. But you have sometimes multiple neurons feeding one neuron, and then the way in the natural world that neurons get activated is you have to pass this threshold of excitation. So if 3 neurons try to give a chemical signal to the output neuron in the real world, if they don't pass that threshold, it will not be excited. It will not be activated, right? So you have to have your resting potential has to be perturbed enough that you pass the threshold. Once you pass the threshold, it becomes activated, and then it goes back to what it was. Obviously, it over-adjusts and then goes back to normal. And it's the same exact thing when you think about our artificial neural networks. You have an activation function, such as here the step function. ReLU is another one that's also good as far as having the minimum threshold to be met. In the step function here, any value that is below 0 will simply not activate the neuron. So if a value comes here, -2, -1, it's always going to be 0. You're essentially below the threshold. Once you hit the threshold, the activation function becomes active, and you're going to return a value of 1 back to the next neurons, right? To the next layer. So this works very similarly to how your brain actually learns. Neural networks are very similar to the brain. Obviously, the brain is way more complex. And we have, again, bioinformatician here in the audience who can tell you a lot more than I can about the complexities of natural systems. Obviously, I'm oversimplifying, but I'm just trying to get the concepts in general of neural networks is that we try to mimic how the brain learns, how you learn, right? And here's, for example, image recognition. If you think about the stimulus that comes through your brain, it'll go through different areas of your brain, and each area will do something. So you have an encoding area in your brain, you have the neural network itself, you have a decoding, and you have a behavior that is sort of triggered. Same thing with image recognition, right? You see certain patterns you have in convolutional neural networks, which are used for image recognition. You have a filter, right? The filter will convolve over the image. Think of it as a filter, like sort of like encoding, maybe, right? So you have a filter that will convolve, and then you feed that. If you do some max pooling as well, you feed that into a neural network, and then it'll guess sort of it'll look at the trends within the pre-processed data, and then we'll send back a prediction. So works, image recognition works, try to work as similarly as possible as the brain, but obviously the brain is way more complex. But if you think about neural networks and their learning, this is sort of a very fun GIF that I saw online. I thought I posted here. You'll see that every sort of pattern will excite or activate certain neurons in your neural network. Same thing as certain things that you experience in life will trigger different areas in your brain or different pathways in your brain. Same thing with your neural networks. Certain numbers or certain events, certain stimuli will simulate only parts of the neural network, right? So number 2 will activate certain patterns. Number 1 will activate different patterns, and therefore will affect the ultimate prediction differently. Same thing with your brain. Certain stimuli will activate different regions of your brain, and so again, very similar to how your brain works. So now I'm going to finish off with just 4 points of why I believe neural networks is really all you need. It is the future. Forget about the traditional models that we talked about, like linear regression and logistic regression, all this stuff, because I can tell you this, neural networks can perform almost as well in all cases. And this, to me, this slide is why I believe, and many believe, that neural networks are extremely powerful. It's because of this thing called the universal approximation theorem. The universal approximation theorem states that for any continuous function f on a compact set K, there exists a feed-forward neural network having only a single hidden layer which uniformly approximates f to within an arbitrary error rate on K. What does that mean? That jargon means? It means that if you have any mathematical function that is continuous, there is a neural network out there that can approximate it. Okay? So there's always going to be a neural network that can approximate the function that you're looking for. So number 1, why try to guess? If you have a data set, why are you going to run a linear regression versus a polynomial regression? Well, you can just let the network figure it out for you, right? That's exactly what the network does. It adjusts its weights, and it can actually approximate all continuous functions. And it's been proven mathematically. You can look it up later, and I've actually done it myself in coding. I published an article about it where I've actually tried approximating a polynomial function. I've actually tried approximating a linear regression, and it's perfectly fine. It's very close, like over 99% in some cases. And so the beauty of neural networks is one size fits all. And so to I think it was Nishan's point, where you're like, which model should we pick, right? You have so many different models in traditional modeling. You have all these different models, you don't know which one to pick. With neural networks, you don't have to pick. With neural networks, let the network learn, and it will approximate whatever function it is. You literally don't have to run any of these other regressions. The neural network will tell it for you. Universal approximation theorem, extremely powerful. And really, you have confidence that with your neural network, even though there could be maybe a traditional model that could beat it by maybe 2%, but the neural network will perform extremely well. I've seen it firsthand. I've worked on a fraud detection model at Freddie Mac. I was able to literally take the top model from Data Robot, and I was able to create a neural network that literally performs on par. And seeing it just triggered me. I was like, whoa. So we paid millions of dollars for Data Robot, and then they gave me the best model, and then I built a neural network that can perform as good as the best model. What do I need Data Robot for? All I need is a neural network. And then it'll figure out everything. It's very easy to do in Keras. Literally, this is all you need to build a neural network. I'm not talking about preprocessing. You literally can build it in a few lines of code. You create a sequential model. You want to create a dense model. You want to create a convolutional layers, whatever you want to do. Very easy to do in Python. I'm not sure about R, Pramod, but I don't want to get into that now. But Python is very easy to do, right? The third point is it's used in all the cool technologies that you use, that you find cool. Self-driving cars use neural networks. Google Home use neural networks. Image recognition, all the stuff you do on your apps use neural networks. And lastly, and I'm going to finish off with that, it is free to use. No money required. You just need to know how to use Python, and you can build neural networks that can approximate any function and perform extremely well. And that's all I have to say for today. I went way over time. I apologize. Hopefully that was informative, interesting, and that's all I have for you guys. Any questions, let me know. Happy to answer them.
Yes, thank you, Keenan. We're going to open this up for Q&A now. If you want to stop sharing your screen, Keenan,
sure.
You can get into Q&A.
Yep.
Yeah, thank you. That was a fascinating presentation.
Thank you.
And I'm glad that we recorded it, because I definitely have to listen to it again to understand it completely. It's pretty deep. With that said, I'm going to do something that we usually don't do, which is essentially promoting our attendees as panelists here. So please feel free to ask your question by unmuting your phone, or if you're on a computer, unmuting your computer, and then please feel free to ask the question directly, or you can send that to us via the Q&A feature on Zoom. Because I do know that there are some machine learning heavy hitters, if I may refer to them that way, on this call. So
yep.
Yeah, please let us know here.
Definitely
any questions, comments.
I said some pretty incendiary stuff, so definitely open to all the questions.
I don't want to name names, but I know that there are some folks here who want to weigh in.
Yep.
Unless they're busy
yep.
driving or doing other things.
No problem.
But yeah, we'll keep the Q&A open for a little bit. Again, if you don't want to speak, use the Q&A button, or just ask the question by unmuting your phone.
Yeah, hello, can you hear me?
Isaac, do you have a question?
Yeah.
Or just put him back in. Go ahead. Yeah, we can hear you. Go ahead.
Yeah. How difficult is it to pull out feature points from a neural network model? Because almost always it's in biology what features, which is often molecules, are causing some type of effect. So they don't just want the prediction. They also want to know what molecules are causing that, because that can be very informative in understanding a disease, a biological state, a drug reaction, etc.
Yep. That's a great point. And are you asking, can we do this with neural networks?
Yeah, so what does that look like with a neural network when I'm saying, okay, so what was the most informative feature? Or,
yeah. That's such a great question, Isaac. Thank you so much for the question. There are definitely ways to question your neural network. I've actually published an article about this, as well as how do you question your models in general. You can use, Python has some packages such as ELI5 or SHAP. SHAP is the most popular one that DataRobot uses as well. Personally, the way I do it is the way a scientist like yourself would do it, which is you keep all your other all your values constant, and you just start varying the one parameters you're trying to look at the importance of, and then you vary it from like minimum to maximum at constant intervals, and then you will see how just that one value affects the total, the ultimate output of the in the network, right? So, for example, let's say you built a neural network to predict house prices, right? And so you're going to use all these different features, such as the number of bedrooms, the poverty rate in the area, and all these different things. And so what you'll do is you'll take each feature and start varying it by keeping everything else constant, and then you'll look at the effect on house prices. And whichever takes the biggest swing on house prices will be the feature that's most important. And you can do this with molecules. For example, you can just say, you can vary the, I guess for you it would be the abundance of the molecule within the cell maybe. And you can go, what if there's none of that molecule in the cell, but everything else is held constant? How does that affect my outcome versus I'm going to max out the presence of this same molecule, everything else held constant? How does that affect my output? And then you do it for every molecule, and you can see which molecule has the biggest effect on the outcome. Did that make sense?
Yeah.
Awesome. Thank you so much. I'll be sure to share more info with you later on that.
All right. Let us know if you have any other questions. And Keenan, if you don't mind, if you would like to share your contact information, if you are able to put that in chat, how people can contact you, that will be very helpful.
Absolutely.
I'll also publish that on our Meetup page. I do have a question for you, actually, listening in there. So I think you spoke a little bit about how you converted some of the models at your company to more of neural networks.
Yep.
So I think my question is, and again, that's probably the reality at many companies, that they have already built, for example, supervised models, which are already in production.
Right.
So do you have any guidance or advice how to go about converting those into more neural network based?
That's a great question. And if the client has a model that's in production, that means that they have data already, right? And if they have built a model, that means they use a training data set to build that model. And maybe that training data set can be used to literally just feed it into the neural network as well. Obviously, do the different pre-processing that the neural network needs, such as a min-max scaler. So neural networks, you need to scale up your data. It doesn't do well with very large values. So you want to definitely have your data either normalized or scaled. And so that might not be the case for an SVM or something else. But I would say use your training data that you use for your production model and maybe try that on the neural network. That will be one. Number two is maybe using production data from your application and then feeding that as well into the neural network. And then compare the performance between your production model and the neural network. Now, if the neural network performs as well as your production model, same level, there's really no need to switch, right? Like, why would you switch if your neural network is doing just as well? Unless you get a lift, then I would suggest sort of replacing both models. Don't know if that helps.
Certainly. Thank you for that, Keenan. Absolutely. All right. We are going to wrap up shortly here if there are no other questions. But again, this will be published on our Meetup page as well as on our YouTube channel. And Keenan, is there a contact email or anything you want to put on chat for our attendees?
I will do so right away. So I'm going to say
Thank you for that.
Yeah, Keenan Moukarzel.
All right. So while Keenan is doing that, I do want to thank Keenan for, I want to say, a very fascinating and well-researched presentation. I like the way that he organized his thoughts, and he kind of convinced us that neural networks is the way to go. So I understand that it may take some time for us to digest it all and maybe get back to Keenan with any comments we have, any questions, feedback we have. Thank you, Keenan. We truly appreciate you coming to our meetup and sharing this information with us. Thank you.
Thank you so much, Pramod. I really appreciate you having me, and I'm looking forward to hearing what the person next week is going to talk about. And then you tell me which one convinced you better.
Yeah. So since you mentioned that, in about 2 weeks, we have another speaker who's going to argue the exact opposite, which is the resurgence of traditional modeling and the death of neural networks. So it'll be interesting to compare and contrast the two, and maybe we'll bring both of them back together for a virtual debate. All right. Thank you, everybody, for joining us. I know that we are almost on time here, so thank you for sticking with us here, and I'll see you all next week. Thank you. Thank you, Keenan.
Thank you so much, everyone. Thank you, Pramod. Have a good one.